read chapter 6 of Bartle and Sherbert. Always a joy to read. Just briefly show the book. So this is the differentiation chapter. Of course, differentiation is always a lot more straightforward. Even I would use the word prescriptive than integration. So your mean value theorem, Rolle's theorem, right here, Rolle's theorem, mean value theorem, and then L'Hopital's rules, which I personally think the way Bartle and Sherbert does it is the best. Breaking it down into cases, the first type is 0 over 0, and then the second type is anything over positive or negative infinity. So the f on top can be anything, but the g on the bottom is plus or minus negative infinity. Requires different constraints, different proof. I love working out L'Hopital's rules examples. They're just a lot of fun to do. Looking forward to doing these problems. Although I'm doing way too much reading right now because I want to finish this book, just because I also want to plug in a little linear algebra later in the summer. So, and then culminating in Taylor's theorem. I love the way Bartle and Sherbert hooks it in to the higher differentiations for polynomials, and then also how hooks it into the convex functions, and then also Newton's method, the way it is explained coming from Taylor's theorem. So that's really chapter 6. I'll show my notes. Slowly but surely this book of notes is getting thicker. And so I think I'm going to try to read the rest of the book. And I may not do problems for a while, but yeah, it's got to be done that way, I think. And then I'll have a gigantic batch of problems to work on. Now, unlike Baby Rudin, Bartle and Sherbert already comes with great explanations, very clean. There are a few diagrams that I drew that are not in the book, because every time that I see a composition, I always like to draw it. But other than that, really, yeah, I like to write out my compositions. Most of what I read it's a close transcription of whatever is in the book, except for a few little drawings. Every time there's a sine 1 over x, cosine 1 over x, that's the reason why all these proofs work. It's because near 0 the function just keeps going like that. Derivatives, slopes. Using the mean value theorem for approximations. The signum function, either the restricted one that ends at 1 or the full one. Then of course L'Hopital's rules. Got a little confused when I was reading the higher derivatives theorem, but then I looked it up in ChatGPT and I was like, oh yeah, I get it now, of course, with a couple of examples. So yes, eventually the derivative at a value is not 0, but all the ones before it are. Okay, I get it. So ChatGPT to the rescue. But I couldn't figure out this second derivative equation. It's a problem. It's exercise 16. It's just taken for granted in the proof for that the second derivative is greater than 0 for a convex function. And so I'll have to work this out. I did not do it right. This is wrong. I'll fix it when I go through the problems. And then for using Newton's method, there is also a previous method called the bisection method. So I went back, wrote it out to understand how it worked again, just to update myself, and then read on Newton's method. And that is the end of chapter 6. Reading.